Okay, so, okay, so this, if I recall, is the last thing we discussed. Am I correct? Yes, no, maybe so? Oh, okay.
From there, we definitely did discuss this.
I'm sorry?
We definitely did discuss this, so.
Yeah, all right. Did we do this example?
No.
No, okay, this is a quick one. Basically, they're asking to convert the pressure given in kilopascals to torr. So it's a typical conversion type problem where we start off with a given value in pascals. And of course, you guys will have access to the table, which gives you the different relationships between different units. And if you consult the table, you'll see that 760 torr will be equal to 101.325 kilopascal, right? That's the relationship between the torr unit and the kilopascal unit. So let's do this calculation. 100.2 times 760 divided by 101.325. And according to my calculation, and please tell me if I'm wrong, but I got rounded off to first things 751.64. And that's what I got. All right. Any question about this? Any questions? No questions? Okay, continuing. So before we talk about the barometer, excuse me, which is used to measure atmospheric pressure. But let's say you have a gas trapped in some container. How do you measure the pressure of that gas? Well, the instrument that is used to measure the pressure of gases is called a manometer, right? So basically, it consists of a U-shaped tube where one end is connected to where the gas is, and the other end is either open to the atmosphere or closed, and we're going to see how we deal with those situations shortly. And mercury is used as the liquid of choice, again, as in the case of the barometer. And I don't remember if it was this class or the other class I teach at Ocala, but somebody asked me the question, why mercury and not any other liquid? And my answer is, I'm going to explain that later, all right? But there's a very important reason why mercury is chosen, because especially since mercury is expensive and other liquids like water could be used, and it's cheaper, but it turns out that mercury is the best liquid for use in the measurement of atmospheric pressure and gas pressure, right? So this is a diagram representing what is called a closed-end manometer, right? So it's a U-shaped tube, as I said before. This end is connected to your gas source, right? While this end here is sealed, right? So what will happen is that when you open up the tap here, the gas flows, exerts pressure on this surface here, on this side of the U-shaped tube, and that pushes the liquid up here, and the pressure of the gas here would be equal to the height difference between the two mercury levels on either side of the U-shaped tube. Now, one assumption that we're making here is that the space above the mercury over here on this side is basically a vacuum, right? So therefore, there's no pressure being exerted on the mercury over here. In actual fact, the pressure is very low, right? Very, very, very low, right? But we're going to assume that it's zero, all right? So if we assume that the pressure here is zero, that means that this height difference will be equal to the pressure of the gas exerted on the surface of the mercury on the right side of this U-shaped tube, right? So basically, all you have to do is use a ruler and measure this value here and express it in millimeters mercury, and that would be the value of the pressure exerted here, right? Now, you can also determine the pressure in pascals if you use this equation right here, right? The pressure is equal to, I don't know if you guys are familiar with the symbol G, which is used to represent acceleration due to gravity. If you have done physics, or if you're about to do physics, then you're certainly going to meet this constant, right? So G times D, which is the density of the liquid, times the height of the mercury level, right? So this represents the pressure exerted by a mercury column. So all you have to do is plug the numbers in. Now you have to be careful about the units because G is expressed in meters per second squared, and you'd have to express the density in kilograms per meters cubed, and H would represent the height of the mercury column in meters. So if you put all those units and numbers together, you're going to get the pressure expressed in pascals, all right? So this is one way of expressing the pressure that is exerted right here, where this mercury column is of a height H or delta H, all right? Okay, so that is a closed-end manometer. Now, we also have what is called the open-end manometer, which is shown here, right? And we have two situations being described on each side. So what I'm going to do is start discussing the one on the left and then move on to the one on the right. So, as you can see, this end is open, right? Which is different from the diagram I showed you on the previous slide. So that will change things a bit in terms of calculating the pressure of the gas that's trapped in this vessel right here. So let's take into consideration the fact that when this is opened up, the gas will move here and then exert its pressure on the surface right here, right? That pressure would be equal to whatever the pressure that will be experienced by anything that is at this point right here. That pressure will be equal to the height of the mercury column, the difference between the two mercury levels, that height, plus the atmospheric pressure that is acting on the surface here, right? And you notice it's called P bar. So the atmospheric pressure is the same thing as the barometric pressure, right? So that's what the bar represents, barometric pressure, right? So therefore, based on what I've just described, we can establish a relationship between the pressure of the gas, the height difference between the two gas levels, and the barometric pressure. And that would be given by this equation right here. The pressure of the gas will be equal to that height difference plus the barometric pressure, and that's what you get here, right? So therefore, if you're asked to determine the pressure of the gas, then you need to know what the barometric pressure is, and you can simply measure the height difference here. The difference or the sum of those two would give you the pressure of the gas, all right? So this is what happens when the pressure of the gas is greater than the barometric pressure, right? This is the equation that you would use. Now, on the right side, things are a bit inverted in that the pressure of the gas exerted here would be less than the barometric pressure, right? So basically, the barometric pressure that is acting on the surface here would be equal to delta H, right, plus the pressure of the gas, all right? So therefore, that's the equation right here. Barometric pressure is equal to the pressure of the gas plus delta H. So if you want to find the pressure of the gas in this case, you'd have to find the difference between the barometric pressure and delta H, and that will give you the pressure of the gas in the case of this situation here. So for example, it says for part B, what is the pressure of the gas if delta H is 100 millimeters and P bar is 760 millimeters. So basically, to find P gas, that will be equal to P bar minus delta H, and then you put the numbers in. So P bar is 760 millimeters mercury minus delta H, which is 100 millimeters mercury. And that would be equal to 660 millimeters mercury. So that's basically how you calculate the pressure of a gas in that situation. All right. Okay. Any questions about this? Any questions? Questions? Okay. Now we're going to get into the explanation as to why is it that mercury is a liquid of choice when it comes to instruments like the manometer and the barometer, right? So here's a question. This question is asking for you to calculate the height of a column of water, and it gives you the density of water that exerts the same pressure as a column of mercury, and it gives you the density of mercury, 760 millimeters high. Let me see if we can erase this thing. So I can. Oh, you know what? Let me do this. Wait. Okay, so yeah, these scribblings, I did that when I was recording a video, so I'm just leaving it there so that I can just use it to explain the answer to this question. Okay, so the question says that the column of mercury will exert the same pressure as a column of water, right? So the first thing I did, two things I did firstly, I wrote down the formula that I gave you earlier, right? Remember the formula I gave you? pressure of a column is equal to the height of the column times G, which is the acceleration due to gravity, times the density, right? And then because the question says that both the water column and the mercury column has the same pressure, I said PW, the pressure of the water column, would be equal to P of the mercury, right? And then what I did was that I wrote down equations, this equation for these two different terms. So in the case of the water, that would be the height of the water times the acceleration due to gravity times the density of the water. And then on the other side of the equation, I would put height of the mercury times the acceleration due to gravity times the density of mercury. Now, because G is the same on both sides, we can cancel it out, right? So that's the reason why we cancel G here and G here. And then because I want to find out what the height of the water column is, right? I divide both sides by the density, right? So the density of water will cancel out the density of water here, and you're left with the density of water on this side here, right? So all I have to do from here is plug in the numbers for the height of the mercury column, the density of the mercury, and the density of the water. And that's what I did right here. 760 millimeters times 13.6 grams per centimeter cube divided by the density of water, which is 1.00 grams per centimeter cube. And when I worked that out, it's kind of cut off here, but the answer became 10,300 millimeters, all right? And this is the reason why we don't use water in instruments like the barometer, right? If you were to use a barometer where water would be the liquid of choice, then you're going to need a tube, which is at least 10,300 millimeters tall or long, right? Now, just to give an idea as to what we're talking about here, 10,300 millimeters is the same thing as 10.3 meters, right? And just to give an idea as to what 10.3 meters look like, my height is just under 2 meters, right? So if you can imagine a tube, which is 5 times my height, for the purpose of using an instrument like a barometer, as you can imagine, it can be very inconvenient, right? For us to have such a long tube. So that's the reason why mercury is a liquid of choice, because in the case of mercury, the tube length that you're going to need is at least, it's going to be about 760 millimeters or greater, all right? So that's the reason why mercury is a liquid of choice. It's pretty much due to the fact that mercury has a very high density, right? Its density is 13 times that of water, 13.6 times that of water. So therefore, mercury is a liquid of choice when it comes to use in instruments like the barometer and the manometer. Okay, so with that said, I'm going to get you started on assignment number 5. So go. And for you guys out there in Zoom, I'm going to publish it now. So let me do this. Files. Assignment. Number 5. Okay, so it's now published for you guys out there in Zoom. So let me just open this up now. And download. Okay, so this is it, all right? So let's look at question number 1. It says perform the following conversions. And they gave you 0.357 atmospheres, and you have to convert it to torr, right? So what's the relationship between the atmosphere unit and the torr unit? Feel free to use your tables that is provided in Canvas. So what would go down here as a denominator, and what would go up top as the numerator?
You put 1 atmosphere at the bottom,
Okay, 1 atmosphere down below, and what goes up here?
you would put 760.
Exactly. So let's see what that gives. 0.357 times 760, And according to my calculation, this works out to be equal to 271 torr. Okay, very good. What about the next one? 6.60 times 10 to the minus 2 torr. Okay, so in this case, what would we multiply by? What would go up top here and what would go below here? Yeah. I'm sorry,
760 torr on the bottom,
760 torr below. And what goes up here?
one end.
Okay, very good. Excuse me. So, let's see here, 6.60 times 10 to the minus 2 divided by 760. And according to my calculation, this gives 8.68 times 10 to the minus 5 atmospheres. Okay, the next one, 745 torr to pascals. Okay, so what goes below and what goes above?
Like, I could see you could do. The first one, you could do 762 on the bottom, and then you would do 1 atmosphere on top.
Okay. But remember now, we're going to pascals. So if you're gonna go this route, you need another conversion factor.
Then that one would be 1 atmosphere on the bottom, 101,325 pascals.
Okay. Pascals, okay. So the torr units cancel out, the atmosphere unit cancel out. So that would be 745 and by 760 times 101.55. So according to my calculation, when we roll it off to 3 sig figs, that gives 9.93 times 10 to the 4 pascals. All right. Okay. B, you're going from 802 millimeters mercury to atmospheres. So what do we multiply by? What goes below, what goes up top? Okay.
Start with millimeters mercury and bottom at 1 on top.
So 760 millimeters mercury below, 1 atmosphere above. And let's see, 802 divided by 760, according to my calculation, that gives 1.06 atmospheres. Because this will cancel out with that. All right. Okay. Any questions about any of these? Any questions? Questions? Any questions out there in Zoom? All right, let me clear this. Let's scroll down. Okay, so these are similar to some of the stuff that we just saw in the PowerPoint. Okay, so let's read the question and see what's happening here. It says, if the atmospheric pressure is 0.975 atmospheres, what is the pressure of the enclosed gas in the left arm of the tube in each of the cases below? All right, so basically what you're saying is that you're gonna have a gas trapped in the left arm of the tube. So the gas is here in each case. All right, so the question is asking, what is the pressure of the gas that is trapped there, right? Now let's look at the first instance, right? We have the gas trap here, right? And assuming that this is mercury, then basically this will be a vacuum, right? Okay, so what does that mean? That means that the H value here, the height difference between the two mercury levels on either side, will be equal to the pressure exerted by the gas. All right, so all we have to say here is that the pressure of the gas is equal to 45 millimeters mercury, right? Because the gas is acting here in terms of exerting its pressure, and it's pushing the mercury up here. There is no gas here, right? So therefore, the pressure of the gas here would be the difference between the mercury levels in terms of millimeters mercury. So that would be the answer for this one. Now, in the case of this one, this end is open, right? So we have the barometric pressure acting here, right? If you remember the example that we looked at in the PowerPoint, we said that all you have to do is look at the pressure of the gas exerted here in relation to the height difference and the pressure of the atmosphere, the barometric pressure. In this particular case, the pressure of the gas would be equal to the barometric pressure plus the height difference. All right. Now they gave you the barometric pressure, which is atmospheric pressure, as 0.975 atmospheres, right? So what we have to do first is convert that to millimeters mercury, because if you're adding these values, they all have to have the same unit, right? So let me just do a quick calculation right here. P bar will be equal to 0.975 0.975 atmospheres multiplied by 1 atmosphere over 760 millimeters mercury, right? So we need to do that first. So 0.975 times 760, and according to my calculation, that works out to be equal to 741 millimeters mercury, right? So to calculate the pressure of the gas here, that will be equal to the barometric pressure that we just converted to millimeters mercury, plus the height difference, which is 78 millimeters mercury. And let's see what that gives. So 741 plus 78. And according to my calculations, this works out to be equal to 819 millimeters mercury. All right. And that's how we do that. Any questions about this one? Any questions? Okay, so if you understood what we just did in the second one, let's see what you can suggest in answer to the third one. Now, please note, in the case of the third one, you still have the gas trap here, but the height difference is switched, right? So again, you're still going to have barometric pressure acting, P bar, acting on the surface of the mercury level on the open end, right? So basically, I want you guys to tell me what's the relationship between the pressure of the gas, the barometric pressure, and the height difference between the two mercury levels. Yes, ma'am. Okay, so what I'm asking for is the mathematical relationship between the barometric pressure, the difference in the height of the mercury levels, and the pressure of the gas. And one hint, let me give you a little hint, based on the fact that the mercury level is down here, that means that the pressure of the gas will be less than the barometric pressure. All right? Okay, so what's the mathematical relationship? Something looking like what we did here.
Is it the pressure plus height of the mercury equals the
Pressure of what?
the atmospheric pressure
Okay.
or not multiplied plus the millimeter of mercury in height or the difference in height is equal to our final result or the value that we want.
Pressure of the gas? You sure
Yes.
about it?
Or
I'm not so sure about that. And the reason why I
Is
said, as I said before, the pressure of the gas would be less than the barometric pressure. As you have it right here, the pressure of the gas will be greater than the barometric pressure because you're adding H to it. So I would not agree with that equation. So let me erase it. Remember, the pressure of the gas in this particular situation is going to be less than the barometric pressure.
is it how about is it the atmospheric pressure measured in millimeters of mercury?
Yeah, it's the same value here.
Okay.
Yeah. So what's the relationship between the barometric pressure, the pressure of the gas, and the height difference? And again, remember, the pressure of the gas will be less than the barometric pressure. Pressure of the gas will be less than the barometric pressure. Yes, ma'am.
So barometric pressure will equal the pressure of the gas plus the height.
Exactly. Pressure of P bar. You're absolutely correct, my dear lady. P bar is going to be equal to the pressure equal to the pressure of the gas plus the height. Exactly. So how do we find the pressure of the gas based on that? Pressure of the gas will be equal to what? Simple algebra. The pressure of the gas will be equal to what? Well,
It will be the pressure of the atmosphere over H.
I'm sorry, repeat that.
So P bar on top and H on the bottom. Like P bar divided by H.
No, it will be P bar divided by H, it will be P bar minus H. Right? And then
Okay.
what comes in, so P bar is, as I said before, 741 millimeters mercury. Minus H, which is 67 millimeters mercury. So 741 minus 67. And according to my calculation, this works out to be 674 millimeters mercury. That's all that is done. All right. Okay, any questions about any of these? Yes, ma'am.
How did you get 741 millimeters mercury?
Because we converted the atmosphere's value given to
Oh,
millimeters mercury.
thank you.
And we had to do that because when you're subtracting or adding these values, they have to have the same units, right? So that's the reason why. Or what you could do, because they didn't specify the units that for what you're asking for. What you could do, I would give full credit if you did the reverse, where you converted these to atmospheres and then added to that. Right? That would be, as far as I'm concerned, just as correct. All right. Okay. Any other questions about this? Any other questions? Any other questions? All right, so let me clear this here. Let me scroll down and see what's next. Oh, okay, so let me go back to the PowerPoint so we can look at the different gas laws. What time is it? Okay, so the first law we're going to look at is Boyle's law, and this law relates the pressure of a gas to its volume, right? And there are several ways of expressing this law, both mathematically and in words. So in words, one way of expressing it is that for a fixed amount of gas at a constant temperature, the volume of the gas varies inversely with its pressure, right? And basically what that means is that basically if you were to, for example, double the volume of a gas, everything else being the same, the temperature and the pressure and the amount of gas being the same, if you double the volume, the pressure would be decreased by half. If you triple the volume, then the pressure will be reduced by a third, and so on and so forth. So this is one way of expressing Boyle's law. Another way of expressing it is that for a fixed amount of gas at a constant temperature, the product of the pressure and the volume is a constant, right? And that is also basically saying the same thing in a different way. And for those of you enrolled in my lab, there's one experiment that you're going to do where you're actually going to see this at work, where the pressure of the gas times the volume is going to be constant, even when you change the volume and change the pressure. When you multiply them together, you're going to end up with a constant value. Now, mathematically speaking, this is how we express it. PV is equal to constant, or P initial times V initial is equal to P final times V final, or I prefer P1 V1 is equal to P2 V2. All right, same thing. All right. Remember that the constraint here is that the amount of gas is fixed and the temperature is constant, right? So those two variables have to be held constant in order for you to see this law at work, right? Now, pictorially, we can represent the relationship between pressure and volume. If you were to plot, as you can see here in this graph, pressure versus volume, and we can see that as the volume increases, the pressure decreases, right, proportionally. So if you start off with a pressure of 4 atmospheres here, and the volume is V, if you were to double the volume, then the pressure would be reduced by half from 4 to 2. And then if you double the volume again, the pressure is reduced further from 2 to 1. And if you continue, you see basically that trend persisting. Now, the graph on the right is showing you a plot of pressure, 1 over pressure versus V. And you'll notice it's a straight line, right? And that's because Boyle's law says PV is equal to a constant, right? So therefore, if you were to rearrange this, you're going to get V is equal to K times 1 over P, right? So V would be plotted, let me rewrite this here. Let me clear this here. We can rewrite this as V over K or V times 1 over K is equal to 1 over P, right? So 1 over K is also a constant, so I'm just going to call it K prime V, or VK prime is equal to 1 over P. So if you were to plot 1 over P on the y-axis and V on the x-axis, you're going to get a straight line curve where K prime would be the slope, and that is basically what's observed in this particular case. Now, here a question is being asked. Estimate the pressure at 3V and 5V. Which plot is easier for making this determination? I would say this plot. The straight line plot would be easier for you to make that determination. because it's a straight line, right? So if I were to try to find out. If I were to try to find out, what would be. Okay, what did I do wrong? Yeah, I'm messing up here, I don't know. All right, let's just continue. So if I were to try to find out what the pressure would be at 3V, what I would do is I would find out what 3V is, which is right here. And then draw a vertical line like this. And then a horizontal line like that. And it looks like here, the 1/pressure will be 0.75. So if 1/P is equal to 0.75, that means that P is equal to 1/0.75, which is 1.33 recurring. And that's how you'd find the pressure based on that plot, right? And similarly, if the volume is 5V, which is about here, you do the same thing. Draw a vertical line, get a horizontal across, and that looks like about 1.5. And you do the same thing, all right? Okay. Try something. Okay. All right. So that's basically the graphical representation of Boyle's law. Okay, so here's a question. It's talking about a balloon that has a volume of 4.50 liters at sea level, where the pressure of the atmosphere is 748 torr. Assuming that the temperature remains constant, what will be the volume of the balloon when it's taken to a mountain resort at an altitude of 2,500 meters, where the atmospheric pressure is 557 torr? Now, let me just say this. So when you're doing problems of this type, you have to identify what would be the initial, based on the information provided in the question, what would be the initial pressure volume, and what would be the final pressure volume, and what the question is asking for. So based on that, it tells you that the initial volume is 4.50 liters. So this would be your P1. The initial pressure would be 748 torr, that would be P2. And then the final pressure is, I'm sorry, that would be P1. I'm sorry, that would be V1. Get my numbers confused. This would be P2. And what the question is asking for is V2, right? So based on Boyle's law, V2 will be equal to P1, V1 over P2. And all you have to do is put the numbers in. So P1 is 748 torr times V1, which is 4.50 liters. And then divide by P2, which is 557 torr, right? And the torr units will cancel out here and here. So 748 times 4.50 divided by 557. And according to my calculations, this works out to be equal to 6.04 liters. And that's basically all that is done. All right? Any questions about this one? Any questions? Any questions? All right, let me just say this before I move on. Let me just say this about solving problems of this type. When it comes to the units of pressure and volume, if you're applying it to Boyle's law, it doesn't matter what the units are for pressure and volume, as long as the units are the same on both sides of the equation for pressure and volume, right? So the units of P1 must be the same as the units for P2. The units for V1 must be the same as the units for V2, right? And it doesn't matter. So for example, the volume could be in liters, it could be in milliliters, it could be in gallons, it doesn't matter. And the pressure, it could be in atmospheres, or it could be in millimeters mercury, or it could be in torrs, it doesn't matter. As long as the pressure units are the same on both sides, and the volume units are the same on both sides, right? And the reason why I mention that is because you could be given a problem where P1 is given in atmospheres, and P2 is given in millimeters mercury, right? So in that situation, what you do is either convert the P1 one value from atmospheres to millimeters mercury, or the other value from millimeters mercury to atmospheres, and then you plug the numbers into the equation, and then you solve it from there. All right. So it's very important that you are cognizant of the fact that the units of the different measurements must be the same in terms of pressures and volumes. Okay, another law we need to talk about is Charles' law, and this law deals with the relationship between temperature and volume, right? And again, it can be stated in words, as you can see here. The volume of a fixed amount of gas at a constant pressure is directly proportional to, and this is very important, directly proportional to its Kelvin or absolute temperature. All right. So what this law is saying is that there is a relationship between volume and temperature, a direct relationship, a linear relationship, but the temperature values have to be expressed in Kelvin. So if you're given a problem where Charles' law is required, you have to convert, and if you're given a temperature in Celsius, you have to convert it to Kelvin before you can plug it into the equation. So as I said before, this is the law stated in words. And before we get to the formula way of expressing it, let me just say something about absolute zero. You may have encountered this in your previous chemistry experience. Basically, the absolute zero value is obtained, it's a theoretical concept, let me just say this first, and it's obtained by extrapolating the graph. When you plot volume versus temperature, you extrapolate the graph until the line cuts the x-axis, right? And this represents a temperature at which the molecules will have no kinetic energy whatsoever, right? Now, the thing about it is that this has not been achieved. Nobody, as far as I know, up until when I checked over the summer, or over last semester, I should say, nobody has achieved absolute temperature. So nobody can confirm that, right? This is just something that is basically predicted to happen based on the observation of how the volume changes with temperature, right? So basically the absolute zero on the Kelvin scale is equal to minus 273.15 degrees Celsius. So basically at that temperature, the molecule should not have any kinetic energy whatsoever, right? So what was decided by the powers that be was to develop a new temperature scale where 0 Kelvin is set to be equal to minus 273.15 degrees Celsius, right? And therefore, based on that relationship, we can write down a formula, write it down here, where the temperature expressed in Kelvin is equal to 1 Kelvin over 1 degrees Celsius plus, no, I'm sorry. Let me erase this here. Is equal to the temperature in Celsius plus 273. For our purposes, we're just going to round up to 360. So 273 degrees Celsius over Kelvin. Okay, let me see something here. What do I see? Okay, so this is going to be Kelvin. Don't know why I'm confused. And this is going to be Kelvin over degrees Celsius. Okay, so that's the formula, right? What's that? Okay. So that's the formula for calculating. If you're given a value in Celsius, you just simply add 273 to it, and that will give you the value in Kelvin. All right. So that's basically the relationship between the Kelvin scale and the Celsius scale based on the adoption of the Kelvin scale, where 0 Kelvin is set to be equal to minus 273.15 degrees Celsius. Now, let me show you graphically what we're talking about. So basically, this is the graph of the volume on the x-axis, on the y-axis, versus temperature in Celsius on the x-axis. Right, to say, you know. Okay, so volume on the y-axis, temperature on the x-axis, right? So if you have a gas, right, let's say at this temperature, and you cool it, right? And you look at the volume as it relates to the temperature. So you record the volume every time you record the temperature. You're going to get a straight line according to Charles' law. Now, what's going to happen is that for pretty much all gases, if the temperature is low enough, it won't be a gas anymore. It will go from a gaseous state to the liquid state, right? So we cannot tell what the gaseous behavior would be below the boiling point of the liquid. So what was decided, or what was done, was that this line was extrapolated to see what would happen if the gas remained a gas below the boiling point, which is not going to happen, but we're just going to see what happens. And what they discovered was that the line cuts here on the x-axis where the temperature is minus 273.15 degrees Celsius. And that is the temperature which, based on this graph, where the molecules, if it were a gas at that temperature, would not have any kinetic energy whatsoever, no translational energy, no vibrational energy, no rotational energy, right? So that's the reason why we end up with the Kelvin scale. So basically, what was decided was that this value right here would be 0 Kelvin, all right? And that is basically what is shown here. Basically, what they did was that they moved the y-axis from here to here. That's where you end up with this right here. So this is also 0 Kelvin right here, all right? And that's how we end up with the Kelvin scale as a result, all right? So that's the lowest temperature possible. And as I said before, that represents the temperature at which the molecules will have no kinetic energy whatsoever. All right. So that's basically that based on Charles' law. Okay, so let's look at this example. It says that you have a balloon again. The temperature is 27 degrees indoors, has a volume of 2.00 liters. What will be the volume be outdoors where the temperature is minus 273, minus 23 degrees Celsius? Now, before we do that, there's one thing I forgot to mention. And that is that mathematically speaking, do this here. Charles' law says that V1 over T1 is equal to V2 over T2. As long as the pressure and the amount of gas remains constant, right? So that is basically what Charles' law is saying, mathematically speaking, right? And again, the temperature must be in Kelvin. So we write it here, temperature must be in Kelvin, all right? Okay, so with that said, let me go to the question now. Question says that the initial temperature is T1, which is 27 degrees Celsius. The final temperature is T2, which is minus 23 degrees Celsius, and the initial volume is V1. Now remember, temperature must be expressed in Kelvin, so we need to convert the 27 to Kelvin, which is adding 273. So according to my calculation, T1 is equal to 300 Kelvin, and in the case of T2, that is 273 minus 23, and that gives 250 Kelvin. All right. So V1 is equal to T1 over T. V1 over T1 is equal to V2 over T2. Right. What the question is asking for is V2. So to get V2, what I would do is multiply both sides by T2, and you're going to end up with V2 is equal to V1 T2 over T1, and then we put the numbers in. V1 is 2.00 liters times T2, which is 250 Kelvin, divided by T1, which is 300 Kelvin. So let's see what that gives. 2 times 250 divided by 300. And according to my calculations, this works out to be 1.67 liters. Because the Kelvin units will cancel out there and there. All right. Any questions about this one? Questions? Okay. The next law we're going to look at is Avogadro's law. This is the same Avogadro that came up with Avogadro's number. And this law describes the relationship between the moles of a gas and its volume. And here's the law in words: at a fixed temperature and pressure, the volume of a gas is directly proportional to the amount of gas it moles or to the number of molecules of gas, right? So there are different ways of expressing it mathematically. We can say that the volume is directly proportional to the number of moles, or the volume is equal to a constant times the number of moles, or the volume over the number of moles will be a constant. Or another way of expressing it is, we'll squeeze it up here. V1 over N1 is equal to V2 over N2, right? So those are just different ways. This is the most useful way actually, right? Oh, I made a mistake here. It should be N2. All right. This here should be N2. All right. Again, there are some things that have to hold constant, namely, in this case, temperature and pressure must be constant, right? In order for this law to work. Now, at this juncture, I want to, this should be reintroduced to you because you should have met this before. The whole concept of standard temperature and pressure, right? And that's because basically, if you want to make some comparisons between gases in terms of, let's say, molar mass or whatever, then you need to make sure that the temperature and pressure is constant while you're determining these properties, right? So again, some people who have the power to make decisions on these things, they have decided that the standard temperature would be 0 degrees Celsius and the standard pressure would be 1 atmosphere, right? Of course, 0 degrees Celsius is the same thing as 273 Kelvin, and 1 atmosphere is the same thing as 760 millimeters mercury, right? So the abbreviation for that is SDP. So if I were to tell you that a gas has a certain, let's say, mass at SDP, then you should immediately understand and remember that we're talking about standard temperature and standard pressure, right? Temperature being 0 Kelvin or 273 Kelvin, I'm sorry, and standard pressure is 1 atmosphere or 760 millimeters mercury. Also, I want to reintroduce to you this concept of molar volume, right? The molar volume of a gas is the volume occupied by 1 mole of that gas, right? The volume occupied by 1 mole of gas is called the molar volume. And it turns out that under SDP conditions, right, and we can actually mathematically prove this, under SDP conditions, the molar volume of an ideal gas is equal to 22.4 liters, right? And that is true pretty much for all gases, right? The molar volume, the volume occupied by 1 mole of gas is 22.4 liters, right? Okay, so with that said, okay, I thought an example was coming up for that, but I guess not. Okay, so let me get into another gas law, Gay-Lussac's law. This law relates to pressure of a gas phase temperature, and basically what this law says is that a fixed volume and mole of gas, the pressure of a gas is directly proportional to the temperature expressed in Kelvin. So again, temperature must be expressed in Kelvin when using the Gay-Lussac's law. In fact, let me just say this. For all the laws that you'll be looking at in this chapter, the temperature must be expressed in Kelvin, right? And that is not only true for this chapter, but for some other chapters as well in the future, that will be the case, all right? Okay, so basically, again, we can express this law mathematically as pressure is directly proportional to the temperature, or the pressure is equal to a constant multiplied by the temperature, or the pressure divided by the temperature is equal to a constant, or P1 over T1 is equal to P2 over T2, right? And again, the pressure units, it doesn't matter what the pressure units are, as long as the pressure units for P1 is the same as for P2, but the temperature units must be expressed in Kelvin, all right? Okay, so that's a Gay-Lussac's law. Okay, so let's look at this example. It says calculate the volume occupied by 4.11 kilograms of methane at SDP, right? So you're given 4.11 kilograms of CH4, and you're asked to determine the volume, presumably in liters, at SDP, right? So basically, we start off with 4.11 kilograms of methane. What I would do is convert that to grams, and we all know how to do that. 1 kilogram of methane below, 1,000 grams of methane above. And then what I would do next is convert from grams of methane to moles. So the molar mass of methane is 12.01, oops. 4 times 1.008 for the hydrogen plus 12.01. So I got 16.04 grams of methane for every 1 mole of methane, right? Now, it should be CH4. So far, we have the moles of methane, but remember the question is asking for the volume in liters. The key to getting the next conversion factor is this right here, SDP, right? And remember we said that under SDP conditions, the molar volume of any gas is 22.4 liters. So we can represent that here in this conversion factor where we put 22.4 liters of methane here over 1 mole of methane. And that cancels with that. And then we do the number crunching. 4.11 times 1,000 divided by 16.44 times 22.4. So roll it off to 3 sig figs. I got 5,740 liters of methane. And that's how that is done. Right? Any question about this one? Okay. So we have learned 3 laws so far. Let me see here. So we learned that there's a relationship between pressure and volume, the relationship between volume and temperature, relationship between volume and the number of moles. So what we can do is combine these laws here, which will become important, especially if all the variables have changed. Because remember, for each of the laws, we said that we hold 2 things constant. So if we combine them together, we're going to get this. PV over NT is equal to a constant, or P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. All right. And if there's anything that's constant, we can cancel them out on either side. So for example, if V is constant, that means V1 is equal to V2, we can cancel those out, and so on and so forth. So it all depends on the type of information you're given in your question. All right. So let's look at this example here. It says you have a flask which contains oxygen, right? It's submerged in an ice bath where the temperature is 0 degrees Celsius. In fact, it tells you SDP, which means that 0 degrees Celsius and the pressure is 1 atmosphere or 760 millimeters mercury. So the question is asking, oh, and by the way, same identical flask on the right, but this time it's in boiling water. The temperature is 100 degrees Celsius, right? So the question is asking, what's the pressure of the gas in the flask here? Now, obviously the pressure will be higher because the temperature is higher, right? So the equation I just showed you is what you're going to use. P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. Now, in this case, we can simplify this equation because it's the same volume of the flask, it's the same flask, right? That means that V1 and V2 will be equal, and therefore you can cancel them out. Now the question is asking for P2. So what I'm going to do is some algebra here. P2 will be equal to N2 T2 times P1 divided by N1 T1. So now we have to identify, oh, by the way, I just remembered something. N1 and N2 will cancel out as well because it's the same amount of gas, right? So this is simplified to T2 P1 over T1, all right? Now, T2 is 100 degrees Celsius, which is the same thing as 373 Kelvin. P1 is the initial pressure, which is 1.00 atmospheres. Excuse me, and T1 is the 0 degrees, which is 273 Kelvin. That's it as far as the setup is concerned. 373 divided by 273. So according to my calculation, this works out to be equal to 1.37 atmospheres because the Kelvin units will cancel out. All right. Okay, any questions about this one? Okay, so. Moving along. Oh, there's a question being asked here, let me. Here it is here. Okay, what pressure would be exerted if the vessel was transferred to an oil bath at 200 degrees Celsius? Okay, so basically the equation that we were working with is that equation, all right? So what do you think? How would you go about answering this question? Basically, you're moving from this to 200 degrees, the temperature changes, right? So I would make this T2, right? And T1 would be the 0 degrees Celsius. If I were to rearrange this, I'm going to get P2 is equal to P1, T2 over T1. So P1 was 1.00 atmospheres. T2 would be 200 degrees. Again, we have to convert to Kelvin, right? So 200 degrees plus 273 will give you 473 Kelvin. Divided by T1, which is the initial temperature, which is 273 Kelvin. So let's see what that gives. 473 divided by 73. So according to my calculation, I got 1.73, and atmospheres would be the unit. So that's it. So basically what we're saying is as the temperature increases, the pressure of the gas increases, which of course we all know already, all right? Okay, so let me move on now to what we call the ideal gas law. So these are the laws that we have learned so far, right? And in each of these cases, as I said before, we hold two things constant. So this begs the question, how do we deal with a situation where all the variables change, right? Well, basically, if you combine the Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's law, you're going to end up with this equation right here. PV over NT is equal to a constant. And that constant is given a special name. It's called the molar gas constant, right? So this equation that we just derived is called the ideal gas law or the ideal gas equation. PV over NT is equal to R. And R is the constant known as the ideal gas constant, as I said before. And it turns out that its value is equal to 0.082. For all purposes, we're just going to round this out to 0.0821, right? Liters, atmospheres per mole Kelvin, right? Another way of expressing it, which is more common, is this right here. PV is equal to nRT. I had some students in the past, they called it the perfect earth equation. I don't think that would help you to remember that, right? But that's the ideal gas law, all right? So basically, this equation can be used if you are given four of these items, three of these items, and you want to know what the fourth one is, all right? Because R doesn't change, but the pressure, volume, the number of moles, and temperature can change, right? Now, in terms of the units, right, very important. You'll notice that the units of R is given right here. It's liters atmospheres per mole Kelvin, right? So this would be the units for this value if the pressure is in atmosphere, the volume is in liters, N is in moles, and temperature is in Kelvin, right? So if these are the units for these different variables, then the units of R would be liters atmospheres over mole Kelvin. But there are other values of R's that exist because of the change in units. So basically, if there are other units, then the value will be different, even though the numerical the value will be different, I should say, even though it's the same R value, all right? So this is basically a summary of the different R values, right? This is the one that is more commonly used, right? At least at this level, where the pressure is in atmosphere, the volume is in liters, and the temperature is in Kelvin. Of course, moles will be the unit for the amount of substance. This one, I don't anticipate us using this one too much, if at all. This one will become important later on in this chapter, and not only that, but in subsequent chapters, right? This one is used where the pressure is in pascals and the volume is in meters cubed. And I'm going to specify when we use this value as opposed to this value. We're gonna use this value more often than using this value, but there are some situations where this value is the one that you have to use under those circumstances, all right? So the important point being underscored here is that you have to be careful about which R value you're gonna use based on the units that you'll be using along with those R values. Okay, so let's look at a couple of examples. The first of which says here is asking for the pressure exerted by 0.508 moles of oxygen in a 15.0 liter container at 303 Kelvin. So this is obviously a straight application of PV is equal to nRT. What the question is asking for is P. So P, I can rearrange this to get P is equal to nRT over V, and then I put the numbers in, 0.508 moles times 0.0821 liters atmospheres over mole Kelvin, times the temperature, which is 303 Kelvin, all divided by the volume, which is 15.0 liters. And let's see what that gives. 0.508 times 0.0821 times 303, and then divide by 15. So according to my calculation, this works out to be equal to, run it out to 3 sig figs, 0.842, and the final units would be in atmospheres, and the reason why is because these mole units will cancel out, these Kelvin units will cancel out, these liter units will cancel out, and you end up with your final units being atmospheres, all right? So that's basically how you do this problem. But please note how I approached it, how I did it. You'll notice that I include the units as part of the whole process, right? That's important so that you can see which units will cancel out. So you'll end up with your final correct unit in your final answer right here. All right? Okay, any questions about this one? Any questions? Any questions? Okay, so another example. Now let me hear what you have to say about this one. This question is asking for the volume, right, of a gas. It gives you the mass of the gas. It gives you the formula for the gas. It gives you the pressure in torr, and it gives you the temperature in degrees Celsius. So how will you tackle this? The equation is PV is equal to nRT, right? The question is asking for the volume. So volume is equal to what? Based on this formula, what is the volume equal? Yes, ma'am. nRT over P. Very good. So now we have to plug the numbers in. Number of moles. How do we get that? Because they did not give us that. So how will you determine the number of moles based on the information provided? Is that your phone? So how do we get the number of moles? Let's start off with that. And again, you guys out there, I know you're quiet, but you can join in. Please feel free to join in this discussion here. How do you get the number of moles? This should be easy, folks. This is high school stuff. Yes, ma'am. Okay, so you have to find the molar mass of C2H6. So let me see here, 2 times 12.01 plus 6 times 1.008. Okay, so I got the molar mass of this as being equal to 30.07. Did I do that right? Let me do the same. 1.008 times 6, right? Plus 2 times 12.01. Yeah, 30.07. Okay. 30.07 grams per mole. Okay, what next?
But then you divide 16 by 30.
Okay, so to get the moles, we divide the 16.0 grams by the 30.07 grams mole per mole. I'm just gonna set it up this way, 1 mole over 30.07 grams, all right? So that's the mole part, the end part here, and then I'm gonna multiply that by the molar mass. I'm sorry, the molar gas constant. I'm confusing my terms today, I don't know why. The molar gas constant, which is always constant, 0.0821 liters atmospheres over mole Kelvin. Okay, what next? What next? What do we multiply by? Yes, ma'am.
Temperature in Kelvin.
Exactly, so 18 plus 273, I got 291 Kelvin. 291 Kelvin, all right? Then we divide by the pressure. Now, the pressure they gave us is in torr. But guess what? We have to do some conversion here because we have the atmosphere unit up here. So we convert from torr to atmospheres by doing this, 1 atmosphere over 760 torr, right? And that's basically the setup. And you're going to see how the units cancel out. The grams will cancel out here and here. The moles will cancel out here and here. The Kelvin will cancel out here and here. Atmosphere would cancel out here and here. And the torr units would cancel out here and here. So we just do the number crunching. 16 divided by 30.07 times 0.0821 times 291. Oops. 291. And then divide by 720 divided by 760. Let me do a second. I think I slipped up somewhere. 16 divided by 3.27 times 0.0821 times 291. Times divided by 760. Okay, so what I got is, and please correct me if I'm wrong, I got, I'm gonna say things. Okay, now because of the 720 here, I have to run that down to 2 sig figs, so that will be 13 liters. That's what I got. Okay, any questions on this? Any questions? Questions? All right, moving along, I think I have another. Oh. Let's go. All right, I'm gonna stop here for today. Let me just say that, I'm going to send you all your grading test one. I just haven't had the time to scan them and send them out to you. So expect it today, and if you get it, and if you have any queries, if you think I've made a mistake anywhere in grading your test, please feel free to contact me about it, all right? But look out for that later on today. So with that, I'll see you guys on Tuesday. What would go before then? Okay, and for you guys out there in Zoom, I'm signing off.